So threads and fasteners are really, really important, and that's what Chapter 8 is all about. When you're designing something and you use standard parts, you can specify the threads and fasteners using standardized methodologies for labeling threads and fasteners. So let's just start the lecture and you'll see what I mean. So we're going to learn how to represent fasteners and threads on an engineering drawing. So hopefully that'll make life easier in the future when you do designs when you start working. And then how do you calculate bolt and screw clearance holes? So it's real important, that you pick the right combination of specifications so that your parts come together easily, as well as they come apart easily if that's what you want them to do, and that there's no undue slop, and also you don't want it too tight either, and it depends what your application is, okay? So we're going to learn about thread symbols as well. You don't have to have very accurate drawings of your threads. You can use symbolic versions of those diagrams, and then that way you can more easily print them out and have them on your drawings so people understand what you're going for. All right, so let's start with some fasteners. So here's an example of a fastener. It's a bolt, right? We're all familiar with these. So nuts and bolts, they're all threaded. Set screws is another kind of fastener. And then you have washers that lock things into place, keys and pins, okay, that sort of thing. So when we talk about fasteners in this course, we're not talking about glue. We're not talking about welding things, okay? We're just talking about things that are not permanent. So that helps with the assembly and disassembly, replacing parts if something breaks. You wouldn't want everything glued on your car, and then if something breaks, you can't get at it, right? Okay. So fasteners and threaded features must be specified in your drawings. Threaded features are specified in a thread note, and general fasteners, you usually give folks the purchasing information so they get the right one and they order the right one. So oftentimes you'll buy a kit online or something and they won't have the standard screws with it because they expect you to go get those yourself or have those on hand. Okay, so here's a screw thread. All right, so it looks like a screw thread, right? It's real easy to see. You've got external on the left and internal threads indicated on the right. And if you specify them correctly, they'll fit into each other, and it'll be easy to screw the part in. It won't bind. Okay, so here's an external thread, right? It's on the outside of the shaft. Okay, and there's usually a chamfer on the end of that, so you can get it started easily. Now, some of you may have had bolts in the past that didn't have a chamfer, so it makes it really tough to get the screw started right. Sometimes you end up cross-threading it, which destroys both the internal and external thread. So you want to design your bolts and purchase good bolts with a nice chamfer on it. Just makes life easier for the assembly. And that's real important as a mechanical engineering designer, that you specify parts that are easy to assemble and they're designed so the assembly process is straightforward. Okay, so when you make an external thread, you got to cut this into the metal somehow. So in design 2, you're going to learn about turning things on a lathe. So if you have a big bolt, you might use a lathe like the picture on the right. And that's actually looks similar to the ones we have in the machine shop. And you can make your threads on that. And that's for specialty parts. Or you can make your bolt and then use what's called a die. That's what's right here on the left side. So that's D-I-E, die. On the right side is a lathe. Okay, so those are two ways you can make external threads. Internal threads, those are the ones like inside of a bolt that your external thread would fit into. Those are manufactured using a tap system. Okay, so the tap is a shaft that has threads cut into them, but only partial threads. And then you put it into the holder here and tighten it up, and you can actually make your thread, your internal thread, by twisting it into it. Now note that it's not a complete thread all the way around. You got to have some space for the metal that you cut to go, right? So it doesn't bind. And also you usually taper the tip off a little bit to get the threads started, and makes it easier. So I don't know how many of you have ever done that. So this is just like a question you would see on a multiple choice quiz. You know, what's this called? Okay, that's a tap. Okay. And do we use it to cut in external threads? No, we use it to cut internal threads. So this is just a prompt for you later when you prepare for any online quizzes and that sort of thing. Here's the thread definition. So we have a lot of things we specify. You can see all of these dimensions that are partially filled out. We haven't put the thread notes in yet, right? But we have something called a major diameter. We have a minor diameter. We have a depth of thread. And we have a pitch diameter. Okay? And that's just some of it. We're going to get some more in a minute. So let's just show what those features are. So if you think about it, you can probably guess what the major, minor, and pitch diameters are and what the thread depth is. So thread depth is how far in it goes. Okay, I don't know if you can see my cursor, right? And major diameter and minor diameter, okay, and pitch are related to how the threads are cut. Okay, pitch is the distance from one thread to the next. So let's look at it more closely. So now you can see the thread depth is from the crest to the bottom of the thread. It's that distance here. So look at where these arrows are lined up. Okay, so that's thread depth. Okay, and then the major diameter is the one from the crest to the other crest on the opposite side. Okay, that makes sense. The minor diameter is from the trough to the trough. Okay, so that tells you how deep the thread is. And the pitch is from the same place in one thread to the same place on the next thread over. So that's the pitch. Okay, now remember that our fonts aren't transferring quite well into PowerPoint. So these little ends you see, those are the diameter symbols. And I just didn't notice them when I was fixing these slides. So just a note for you guys. So when you see these little ends, that's the diameter symbol, the circle with the line through it. All right. So there's some more thread definitions. We have the crest, the root, and the side. So let's take a look at what the crest, the root, and the sides are. Okay, which one do you think it is? I think 3 could be a crest. The root, it might be 4. And the side is probably 9. Let's see if I'm right. Oh yeah, so the crest is the top of the thread. The root is the bottom. I always want to call it the trough, but it is called the root. So crest and root, and then the side of the thread. So you can see if you're designing bolts and things like that, you can have different angles, which is number 10 actually, which defines the side a little bit differently. You can have different roots. You know how wide the root is? And different crests, how wide or pointy the crest is. And of course, you want these to match, to fit with whatever internal thread you're going to put this bolt into. And then we got some more things. We got pitch, angle, so pitch, angle, screw axis, that's what's going down the middle here, and lead. And lead is related to pitch. It's the distance the screw thread advances actually when you do one turn. So when I turn the screw one revolution, how far in does it go? That's what they call the lead, okay? So in industry, we used to have to maintain lead screws on our steppers for precise movement of the stages in our photolithography tools. So those screws were called lead screws, and they were very precisely made. The whole point of those was so you can move a large stage back and forth to nanometer resolution and movement. So that was pretty cool. Okay, so again, we got pitch, angle, and screw axis. So let's take a look at those. So there's the pitch, there's the axis, there's the angle, okay? And then how far it goes in one turn is the lead. Okay, so if you had to choose between A, B, and C or D, which one is the pitch? You can type it in the chat box if you want to. I'm not going to grade these, but think of it in your head. And then we'll go to the next question. What about thread depth? Would that be A, B, or C, or D? Thread depth. Any ideas? Oh, nobody. Okay, someone's got it. B, right? It's the depth. So it's from here to here. Remember how we did dimensioning? You could point at it from the outside or go from the inside. Let's see, like that. You either have your arrows go like this or your arrows go like that, depending on how much space you've got. Okay, so that's your depth. And the minor diameter, anybody want to venture to guess what that is? Is that A, B, or C? Someone take a stab at it. A. All right, excellent. So it's the minor diameter. So it's from the root to the opposite root, right? That's the minor diameter. All right. So here's some more thread definitions. So you're all familiar with right-handed and left-handed screws, right? Most of the screws we deal with and bolts and things like that are right-handed. Okay, no offense to left-handed people, but they just call them right-handed screws. It's righty-tighty, lefty-loosey, right? So you tighten up the screw by turning it, what would that be? Clockwise to me, right? So when you turn it clockwise, the lead goes in, right? So if I turn it this way, the bolt will come towards you. Okay, if I turn it the other way, loosey, the bolt will go away. Okay, so that's a right-handed screws. But there's some examples where you might have to use a left-handed screw. So that way, when you tighten it, instead of turning it this way and having it come in, you're going to turn it, let's see if I can do this. You're going to turn it lefty, and it's going to go in. And then when you turn it righty, it comes out. And that's from my perspective. So you can kind of think about it from your perspective, okay? So left-handed screw you might put into something that turns in a way where it would unscrew itself, right? If you had it tightened to something that's rotating, you could unwind itself, right? So you would do the opposite screw thing, so it always wants to stay tight. And an example of that, a classic one, is a bicycle. So you have a left and a right pedal. If you've ever put bikes together, you'll see that the pedals are labeled left and right. And the reason they do that is one's a left-handed screw and one's a right-handed screw. Otherwise, one of the pedals would always fall off. Okay, and if you try to put them on backwards, like you don't pay attention to the instructions like most engineering students do, because it just seems obvious, you might end up trying to put it in on the wrong side and then realize that the screws don't match. Okay, so there are some examples of where you would use left or right-handed screws to keep things from unwinding. All right, so there's lots of different kinds of threads. We're going to talk about two main types, uniformed and metric. Okay, of course we got to talk about metric. All right. So the thread form choice depends on what you're going to use it for, the length of engagement, how much load it's got to take, etc. So you might have fine threads in some applications and really coarse, sturdy, heavy-duty ones in other applications because there's a greater load. So here's some examples of different thread forms. So here's a unified screw thread. That's in the first row here. It's for general purpose. This is typically what you see on most screws. And the ISO system also has a very similar general use thread, but it's in millimeters, right? It's a metric version of it. Then you have a square thread. This is if you have to transmit a lot of power. You would do more of a square type of thread, so they don't strip out as easily. The Acme thread is stronger than the square. Okay, it's trapezoidal in nature. Okay, so it can carry more load. And then the buttress, this is kind of what you see on a truck jack. Okay, or maybe a ratcheting system where you go in one direction, right? You want a lot of contact area here to pull this to the right, this system, this ratchet to the right, and then when you pull it one tooth, you come back to the left over and grab the next tooth and then pull it to the right. So here's an example of that. This is on a micromotor. So this this thing here is on top, and it's pushing back and forth. This is going left and right. Okay, this frame here, and pushing this little external thread, I guess you can call it, to the right and then to the left. And what happens is it advances this ring on the outside in one direction. So you can take a lateral motion, a left-right motion, and turn it into a rotary motion using this kind of system. And that's using the sawtooth kind of tooth system. Okay, thread system. Here's another micromotor example. This is called a torsional ratchet actuator. Sandia invented this. Basically, you have comb drives here, so you put opposite voltages on the combs, so they attract each other. And in this case, since it's rotationally oriented, you have one set of combs turn relative to another set of combs, in and out, in and out. It does this toggling back and forth, right? Back and forth, back and forth. And if you look closely, there's these little, what do they call them? Drive pawls that pull. You can see one here. I'm trying to circle it with my cursor. So this one pulls the tooth over one tooth, and then when this other system snaps back, that drive pawl jumps over the tooth and goes to the next one. So this outside ring will go counterclockwise. Okay, so let's take a look at a close-up. So here's a drive pawl. So when these two sets of teeth come together, that means one thing is rotating relative to the other. So this frame, this interior frame, is going to move counterclockwise or to the left. This is going to move to the left and drive this ratcheting ring one tooth over. And then this will snap back and this will jump over to the next tooth. Okay, so you can look at these videos online. As Sandia has they call a MEMS gallery, where they show these things actually working. Okay, and this little flexure right here is on the order of a micron, so 1/100th of the size of a human hair. Okay, so you can make really small mechanical things as well. All right, so how do you make screw threads? Well, you have an external and an internal. Okay, so The tap drill hole is a little bigger than the minor diameter. So you're gonna drill a hole to make your internal thread. Then you're gonna use a tap to cut the threads into it. So you make a cylindrical hole, and then you use that tap and screw it in to make the threads. And you want that tap hole to be slightly bigger than the minor diameter of the thread you're going to cut inside of this internal thread. Okay, so here's the minor diameter, and you want that tap drill slightly bigger than this minor diameter. And the reason is as you're threading it, you want a little bit of space between the external minor diameter and the internal one so that it doesn't bind up. Okay. Okay, and then the tap hole you make is going to be a little bit deeper than the actual threads that you need. And that's because, if you remember, the tap has that tapering on the end of it. Okay, so I got to fix this slide. But it basically says, why is the tap hole longer than the length of the threads needed? Okay, because of this. Remember the tap. Okay, this gets your thread started, and then you cut these threads. These are the ones that are going to actually be engaged, right? That when you cut it. So this bolt will go in about this far, and then you have some extra hole there. Okay. So for external threads, we use what's called a die. Okay, and so we have a shaft, and then we start turning the die onto the thread, and we cut the threads that way. And you can buy tap and die sets that are designed so that the external thread and the corresponding die you use for that will cut a thread that'll fit the corresponding tap. Okay. So far, no questions. I hope you guys aren't sleeping. So drawing screw threads. So there are three methods to represent different types of screw threads. There's the detailed, which we've been looking at, that looks like a screw. And then you have a schematic version, which is less detailed, and a simplified version. Okay, and you can get away with simplified if you have a good screw note, right, a thread note. So this is the detailed representation. It looks like a screw. Okay. The pros and cons of this, well, think about it, right? It's a little harder to draw. Okay, that's a con, especially in the old days when you had to draw everything by hand. And it might be more complex than you need to communicate your idea. Okay, so that's another con, but the pro is it looks like a screw. Okay, so there's some pros and cons, and then so we had the detailed version. Now this is the schematic. So you can see this looks a little bit different, but it's still giving you enough information so you can specify the pitch, the chamfer, minor and major diameters, and the thread length. Okay, so you could schematically draw your screw threads this way, and it would be detailed enough that your machinist could make this part. Okay, so the staggered lines are used to represent the thread roots and crests. Okay, so that's pretty straightforward. Pros and cons, doesn't look like a screw, so it's a con, but the pro would be it's really easy to draw. Okay. Rules of use for schematic threads. So how do you use these things? Well, it shouldn't be used for hidden internal threads or sections of external threads. Okay, you can do a section of an internal thread and spec it. Okay, but you wouldn't do a section of an external thread. Okay, so this is kind of what it would look like if you went from the schematic all the way down to the simplified representation. Okay, so this is just showing the bare minimum, minor and major diameters, thread length, and chamfer, and then you would put a note in as to indicate what the pitch and all of that is. Okay, you'd specify it in a thread note from one of the standards. Okay, let me see how we're doing on time. Oh, we're doing great. So the simplified representation has some pros and cons. The pro, it's real simple and fast to draw. Con, doesn't look like a screw. Okay, so here are some examples of simplified internal threads. Okay, whoops, let me go back. Okay, so you would draw it in this manner, and you'd kind of know what the end of the hole looks like here. You would put the pitch and the thread length in, major and minor diameters. It gives you an idea of how to drill it and then what kind of tap to use. Okay, now for a short quiz for no points. All right, so what type is this? A simplified, schematic, or detailed? Someone guess. Okay, schematic is correct. Good job. What about this one? Simplified, schematic, or detailed? Yeah, figure the top one is A if you're going to use a letter. Good job. You can assume that. All right, what type is this one? Yeah, detailed. All right, so we learned some terminology today. The big thing that you're going to really have to deal with the homework is looking up things in thread tables. So the thread tables are in the appendix of your book. Okay, I might provide some tables as well on the homework. I don't remember. I'll have to check that out. But hopefully you all have your book at home. Okay, and then you can look up on the thread tables, if someone gives you the thread specifications, what the pitch, the minor diameter, and the tap drill diameter is, and how deep to drill and all of that. So that's what the machinists do. So the engineers will specify what type of thread to do, and then the machinist will know how to make it, how to manufacture it. Okay, so here's an important note to help you with your homework. If screw thread tables are not available, the minor diameter can be approximated as 75% of the major diameter. So 3/4. So if you know what the major diameter is and you have to calculate the minor diameter, use 3/4 if it's not in the table. Okay, and sometimes you do that when the threads get really, really big. All right, well, let's talk a little bit about unified threads. So here's a simplified drawing, and this is how you would say how to make this. Okay, so this would be in inches. Unified threads are inches. Okay, so we need to identify the size of the thread form. Oops. So identify the size and thread form in a thread note. This is the thread note. So we've got a 1/2 inch, and that would be the major diameter. Okay, so you can actually look up what the minor diameter will be from the thread table. So 13 UNC-2A-RH. Okay, and we're going to talk about what each one of these things means. Okay, so RH, you can probably guess, is right-handed. And typically you don't put right-handed. You assume it's right-handed. So you don't only put left-handed in if it's going to be different. Okay, so here are all the different parts, right? So this would be for an internal thread. We've got 3/8, 24, which is threads per inch. The major diameter is 3/8 of an inch. Remember, we're doing unified, which is English system. Thread form in series, so UNF. So I think that stands for unified fine thread. Okay, so they have fine threads, coarse threads, that kind of thing. There's a thread class involved. The letter indicates if it's external or internal, and then you have left and right-handed. And then in the case of an internal thread, you need to put a depth in there. So this is the depth of the threads. Okay, it's not the depth of the hole. The hole will be deeper than that, depending on what tap you're using. Okay, so I'll take a look at that, kind of let that sink in. All right, so here's some unified threads in inches. Okay, so we've got our major diameter. That's the largest diameter, remember from the schematics earlier on. Threads per inch, that gives you some indication of the pitch. How much space is there between crest and crest or root and root of your thread, okay? So in the English system, we do threads per inch. So how many threads do we have in an inch? In the metric system, we do millimeters per thread. Okay, so one is the reciprocal of the other. Okay, but they're related. Okay, so threads per inch. Okay, and so that's what we're saying here. Threads per inch is equal to 1 over the pitch. Okay, and you should be able to calculate the lead from the threads per inch. So if I have so many threads per inch, how far do I go? If in one turn. So if you have 10 threads per inch, that means in one turn you go 1/10 of an inch. And that might be important if you're using a threaded system to position something relative to something else. Then you might need a controller to control the motor that spins the thread or the lead screw so you can control the positioning of something to high accuracy. So these things are important when you're designing. Okay. So UNC is Unified National Course. That's general use. UNF is Unified National Fine, where you want a little bit tighter thread. And then you have Unified National Extra Fine. Okay, so sheet metal screws are kind of like that because you're only threading something that's very, very thin. Right? So those are real easy to strip out if you've ever worked with sheet metal and sheet metal screws. So you don't want to have your power drill. You want to probably tighten those sheet metal screws by hand so you can feel it because it's very, very easy to strip those out. Okay, next one. So the thread class, that's this 3 here. Okay. So the closeness of the fit between the two mating threaded parts. So it gives you an idea of the gap between the external and the internal thread. So a thread class of 1 is a lot of tolerance. And that's if you're just putting things together quickly, okay, or wanting to take it apart very quickly. So you have a generous tolerance there. 2 is the standard normal production, and then 3 is high accuracy. So sometimes they won't even put this in here. Okay, the 1, 2, or 3, and if that number is missing, you assume it's a 2. Okay. So here's a close-up of the thread note. So think about it. Is this for an external or internal thread? Well, if it says B, okay, it's an internal thread. And A is external threads. And then you have right-handed and left-handed. That goes without saying. Okay, and then you've got the depth of thread right here. So this was an internal one because it has a depth associated with it. So that's what the B is it says it's an internal thread. Okay, because we have a depth. So now the thread depth is given at the end of the thread note and indicates the thread depth for internal threads. This is not the tap drill depth. You're going to actually drill the tap drill depth to be greater than 0.5 in this example because we've got that tapered part of the tap that's got to go past or where the thread depth would be. So if the thread depth is 1/2 inch, and then you've got a 1/4 inch at the beginning of your tap, then you'd have to go 3/4 inch in with your pilot hole to get your thread started, okay? Okay, so thread class is assumed to be 2 if it's not in the unified thread note. Okay, so if there's nothing there, it's a 2. And everything is considered to be right-handed unless otherwise noted. Okay? All right, let's do some examples. Time flies when you're having fun. So here we got a thread note. We broke it out into a column, a list of different parts to it. So we got a quarter, 20, UNC, that's what, Unified National Course, 2A, right? Is it internal or external? And then RH, what handedness is it? So is the 1/4 a major or minor diameter? Anybody want to guess, A or B? Okay, yeah, it's the major diameter, good job. Okay, so it's a 1/4 inch. All right, so what about the 20? Is that a pitch or threads per inch? Remember, pitch is the distance between threads. So when we're doing a unified spec, an English spec, one for inches, is it A or B? Anybody want to guess? Think about it. All right. So it is B, threads per inch. Okay, unified course or unilateral connection. You guys might be able to figure that one out. And then this is a thread class or normal production or both A and C or D, none of the above. Oh, you guys are saying B, huh? It's C, I believe. Right? It does give you the it's normal production because it's a 2, but it's also a thread class, right? Okay. And then if it's not listed, like they didn't have to list it there. So is the A for external or internal? We had a confusing slide earlier, so I can understand if you're confused on it. It's an external thread. Okay. And then that's easy, right? Required hone or right-handed? A or B? E? It's right-handed. Okay. So now you kind of saw what a unified national thread note looks like. Okay. Now there are tables of these things, right? So you can look them up and then get the major and minor diameters and all of that from there. And how the tap drills should be and whatnot. And these are in the appendix in your book, Appendix B. You can also look them up on the ASME thread tables. I think only the old ones you can look at. The new ones you have to buy pretty much because they're copyrighted. But I think there's some old ones around, and there's always charts around that people have posted, so you can always find it there too in the future if you don't have your book with you. And you know, there are tables like that posted all over the machine shop. Jason uses all the time. Okay, so standard screw thread tables are available in order to look up the major diameter, the threads per inch, and the minor diameter and tap drill size from that information. So let's look at an example. We want to make this external thread a number 10 fine thread. So let's go to the tables. Okay, this is nominal size in inches, right? This is a number 10 screw. So if you ever go to Home Depot or something, have to buy screws, They'll have a number 10, number 12, number 8s. Okay, so that's a nominal size indicator. Okay, so a number 10 screw has a basic major diameter. That's the outside of the thread. That's the crest. Is as 0.19 inches. Okay, the threads per inch for a number 10 is 24 threads per inch for the coarse. If you do a fine, it's 32 threads per inch, and they don't even make it an extra fine. Okay, so then you'd say, well, how do I tap it? So I buy a bunch of bolts. I'm going to put two pieces together. I need to tap into the other thing I'm screwing it into. Then you would get a tap drill diameter of 0.1495. Okay, so now you know how to do the tap the drill, right? Or drill for the tapping hole. Okay, so now you can figure that out. So this is a 10-32 UNF. So let's go back. It's a number 10, and we said fine. Okay, so here's the fine. So number 10, 32 UNF. Okay, so it's a number 10, 32, because it's fine. We got 32 threads per inch. If we wanted a coarse, it would be a 24. Okay, and then the rest of this is telling you where to find the other information you may need. Okay, is the major diameter 10 inches? No. The 10 is the major diameter when you look it up. So it's a number 10, which I think was like 0.19. Okay, so let's go back and look at it. Number 10 is 0.19 inches. Okay, so it's 0.190 for this this specification at 1032 UNF. So you would go look on the table and you would find the major diameter. So your homework is like that. We'll give you these numbers. You got to go look up those. Or we'll give you a couple other numbers, and then you have to tell us what type it is. Okay, so it's just filling out a bunch of tables. So you might also be asked, what's the minor diameter? Okay, so we can look that up. Okay, so it's a 1032 UNF. We already found that out. How would you figure out what the minor diameter is? We know how to drill the hole, right? That's the tap drill. But that's going to be a little different, isn't it, than the minor diameter? Okay, so for an external thread, you could use that equation on the top. So you would take the pitch, 32, that's what pitch is, multiply it by 1.0825, and then take that number off of the major diameter, which is given as 0.19, and that'll give you the minor diameter. Okay, that's pretty straightforward. So always look at the top of the table, right? That gets a lot of people in the homework. They don't see that at the top, and then they're emailing me questions. Well, how do I figure that out? Okay, so you do the math, it's 0.156. Okay, so let's go back to this, 0.156. That's a little different than the tap drill diameter. In fact, the tap drill diameter is a little bit bigger than that. Okay. All right, so let's jump to metric threads. So you're going to have to think about this a little bit, maybe play with some nuts and bolts. If you got little kids, you know, you may get the big ones for them to play with, right? You get a big nut and a big bolt. Then you can teach them all about fasteners when they're like 9 months old. Anyway, so metric threads, very similar than the unified threads. The pitch is a little different the way they define it. Instead of threads per inch, they do millimeters per thread. Okay, so we have a pitch diameter which is a little bit different because you do a minor and a major diameter for the unified system. In the metric system, you do a pitch diameter. So you're splitting the difference, okay? You're splitting the difference. So it's a point where the distance of the space is equal to distance of the threads. Okay, so where this space here is the same as this space here. Okay, that defines where the pitch diameter is. So that would be from here to here. Okay, so the crest and the root lengths are the same if you cross-section it. Okay, where the distance of the space is equal to the distance of the threads. That's the pitch diameter right here. So you can see how they define it in metric. A little bit different. It's not the minor, it's not the major. It's kind of like splitting the difference. It's not quite splitting the difference because you can imagine if you have a steeper one and a shallower one, that pitch diameter is going to get bigger or smaller, right? So here are the metric thread note components. So you start off with an M, and that clues you in that it's metric right away. If it has a number leading off, it's not metric. It's what do they call it? A universal national specification. Okay, and then the second number after the M, or the second character after the M, is the major diameter. All right, and then you have a pitch. So the pitch is in threads per, not threads per millimeter, but millimeters per thread. Okay, and then you have tolerance classes. So it gets a little more complex here. Right, we have a pitch diameter tolerance, a crest tolerance with a major diameter indicator, and then of course you have left and right threaded, and you have thread depth as usual. How deep do you want the threads to go? Now the hole's going to be deeper. So put the M before it, that tells you it's metric. Then you got the major diameter. Okay, that's the largest diameter. So if it's a hole, an internal thread, it's the biggest diameter, right? If it's an external thread, it's the biggest diameter. Okay, pitch, millimeters per thread. Tolerance class. So we got a number, 5. Okay, that's the tolerance grade. And the letter is the tolerance position. So the tolerance grade basically means the smaller the number, okay, the smaller this number is, it's a tighter fit. So as the numbers get smaller, the fit gets tighter. The tolerance position specifies the amount of allowance. So the uppercase means it's internal, and lowercase means external. So these are internal threads. Okay. All right. So here's a general purpose. Let's see, what was this previous one? Oh, right-handed and left-handed, that goes without saying. Depth of the thread, already talked about that. You can leave off the right-handed, RH, but if it's left-handed, you've got to put it in. Okay. All right, here's some more examples. So if you have an M10 by 1.5 4H 6H RH, okay, and these are supposed to be lowercase, didn't translate well. Okay, so M means metric or machine. Any guesses? A or B? A, very good. 10, is that a minor or major diameter? It's a major diameter, but it's 10 millimeters, not 10 inches. The pitch, is it millimeters per thread or threads per millimeter? This messes some people up. Millimeters per thread. Okay, think about it, right? If it was threads per millimeter, that's pretty tight. Okay, that's pretty tight thread. That's the pitch diameter tolerance. And that's the crest or major diameter tolerance. Okay, so pitch is the first one, pitch tolerance, crest tolerance. And these are supposed to be smaller case, meaning that they're in external thread, I think. Maybe I got it backwards. Let's see. So these are supposed to be external threads. These are supposed to be lowercase. I apologize for that error, but you see it down here, okay? Internal or external? It's external because these are lowercase and it's right-handed. Okay. So make sure you pay attention to that when you're looking things up on the tables. All right, standard screw thread tables are available in order to look up the major diameter, the pitch, and the tap drill size, and that's also in B. So if you got an M16 internal metric thread, what are the two available pitches? Tap drill diameter and corresponding minor diameter for the mating external threads. So that's a typical homework question. So you go look at the table, you find M16, got M16 by 2. Okay, tap drill is going to be 14 millimeters. It's telling you what it is. That's the diameter of the tap drill. Okay, and that's for general purpose. And then for fine, right, you're going to have a few more threads per millimeter or smaller millimeter per thread because it's finer. Okay, so this would be by 1.5. So that means 1.5 millimeters per thread. That'll give you a fine fit. And in that case, your tap drill diameter is going to be slightly bigger. Okay, so make sure you find these pages as you're going through the lecture later on. Okay, so let's take a look at this. Right, so what do you think the pitch is going to be? Okay, for an internal metric thread. It's going to be 2 or 1.5, depending if it's fine or not, right? The tap drill diameter is going to be 14 or 14.5. So let's go look at this. So 14 for the general purpose, 14.5 for the fine. 2 millimeters per thread and 1.5 millimeters per thread. So the finer it is, the closer the threads are to each other. So it's distance for each thread. The English system is the opposite. Okay, will the minor diameter be smaller or larger than the tap drill? Any ideas? So here's my tap drill. What do you think my minor diameter is going to be for the external thread? It's going to be bigger or smaller? Let's see. Okay, this is where approximate minor diameter comes into play. So you're going to drill, or your minor diameter for the external thread is going to be a little bit smaller than the tap drill diameter. Okay, you need that extra space. All right. So for this, which is the more fine thread? I hope I didn't confuse you earlier. So the finer thread, remember we're talking about metric. So we got a pitch of 2 something or 1.5 something, which is finer. Okay, B it is. All right, so here is a 16 millimeter diameter coarse thread. And what does the thread note look like? It would look like this, right? If it's by 2. If it's fine, you would have by 1.5. This would be a 1.5. Metric, 16 is the major diameter, and this is millimeters per thread. And we're coarse, so it's going to be the bigger one. Let's go ahead and do drawing bolts. And then what we'll do is, if I can't finish this lecture today, I'm going to go ahead and finish it solo and post it, okay? So probably by tonight or tomorrow, it'll be posted. So bolts are a little bit different, right? We've got to define the head of the bolt. We already know how to define the threads. So another thing you're going to have to learn to do if you're designing a lot of different parts that get assembled or machines that get assembled, you're going to have to define the bolt heads. So this is a hex bolt, right? There's 6 sides. So typically the width of the bolt or the hex head is 1.5 times the major diameter of the bolt. Okay, you want it a little bit bigger. Okay, the bolt thickness, the part that's on top, okay, that thickness is going to be 2/3 the diameter typically. Okay, and then it shows you the different angles for the sides, and it's going to be 60 degrees, right? 6 times 60 is 360, so because it's a hexagonal bolt. Mostly they're hexagonal. That seems to be the standard. You might have special cases where you do something different. Okay, then you've got bolt and screw clearances. So you might have a bolt attached to different parts this way. So you'll have an internal thread here. Okay. And then the bolt has an external thread. And this plate that you're trying to attach to this bottom piece doesn't have any threads, but this bottom piece does. So you've all seen that. You take a bolt and you put 2 pieces together, and one piece isn't threaded and the other piece is. So how do you define that? Well, you have to define the C and the D diameter. So the C diameter is the bigger one for the piece that's on top that you're going to, attach to the bottom plate. And it's not threaded. So there's specifications for C for this kind of bolt and thread system. And then D gives you an idea of how big the shaft is. Okay, this part. It's the major diameter, actually. Okay, and then how much clearance you have between C and D and whatnot tells you if you have a normal, close, or loose fit. Okay, so let's take a look at some of the tables. This is right out of your book. So you got metric clearances for D and C. Remember, D and C are these 2 dimensions. Okay, so if you have a diameter in the metric system of 1.6 millimeters, that means your clearance hole is going to be 0.2 of a millimeter bigger than that. Okay. And then if you have an M2, 2.5, et cetera, all the way up to M100. So a 100 would be a 10 centimeter diameter bolt. That's a pretty heavy duty bolt. And then you'd add 7 millimeters to it to get C. Okay, so if your major diameter is 100 millimeters, right? What would your hole clearance be? You got to add a C to that diameter. Okay, 7 millimeters to it. All right, and then you have the same kind of thing for inches, except you have 1/64th, 1/32nd, 1/16th of an inch, etc. Okay. And then sometimes you want the screw heads or bolt heads to be flush with the surface. And when you do that, you have to define this depth here. And it's got to be a little bit deeper than the bolt head height. Okay, and in this case, you'd probably put a nut on this end and bring it together. That's one way to do it. So now you've got D1 and C1. So D1 is the diameter of the bolt head, and C1 is the diameter of the hole that the bolt head fits into. CH is the depth of the hole, and H is the height of the bolt. Okay, so typically CH equals H plus a 16th, or 1.5 millimeters. And C1 is D1 plus 1/8. So you'll typically know what your bolt that you've specified in your drawings, and you will drill the holes accordingly. Okay? And that's to allow you to have the holes or the bolts flush to the surface. So you look these things up. Okay? So that's why this homework set and quiz, like online quiz, which is just duplicating the homework set and entering it into the quiz, is open book, and it lends itself well to that because you're never going to remember all of these rules. Okay. There's a question here that just popped up. What is finals week going to look like for this class? So I'm going to just make these due during finals week, these assignments. There is no final. Okay. So just everything has to be in probably in the middle of next week, right? I think I've got some dates set, but I'll open up chapter 8 tonight, and then you'll be able to judge it. Okay. I might push it a little bit towards the end. It'll be simple, but you got to do the homework, right? You got to go through the lecture slides, refresh your memory how these things are specified, and then do the homework sheets, right? So when you open up the quiz, it'll only give you a certain amount of time, because I don't want you doing the quiz when it's open. I want you just referring to your homework sheets, because you'll have everything, all the answers will be on your homework sheets. Okay, so you'll just be transcribing numbers. Of course, you're not going to transcribe the 300 or so that I have you do, or 100. You're going to transcribe like 10 of them. Okay, so you got to fill out those sheets first. Okay. So that's all I got for today.